we can actually think of it as one node and then a smaller linked list. And again, that would be the recursive definition was to actually print the first element and think of to print the next, all the elements of the smaller linked list. And the base case is when the recursion will stop when you actually reach null, or when you even started off with a null when you have an empty linked list. The factorial is what, is the product of all the first n numbers. So basically n factorial is n multiplied by n minus 1 multiplied by n minus 2 all the way down till 1. So again, you have a recursive definition for factorial. It's a very, very common mathematical formula where, factorial is written like this: n factorial, which is equal to n times n minus 1 factorial, which is the same thing as this one. And this is very similar to the formula for the sum. So in the sum, what you were doing is you were just simply adding all the numbers from 1 plus 2 plus 3 till n. In the factorial, you're simply multiplying all the numbers 1 times 2 times 3 all the way till n. But they can easily be translated, as you can see, in their respective recursive formulas. And then eventually we'll learn how actually we use a stack of function calls to visualize recursion. Incidentally, we will be using a stack soon, but let me tell you first what a stack really is. A stack basically is, it's a data structure that we will begin learning next week, but I'm not sure if you have seen stack as a data structure, but uh, in just the general English language, stack also means like, just a pile of any objects. So for example, a pile of books that you have on your table. So supposing you're cleaning your table and then you want to store, like, in a neatly pile of books and pile of notebooks or something. So you have this a mathematics book over here, a biology book over here, computer science 1 over here, computer science 2 over here. You have these books, right? So we will just refer to this as a stack of books. And then when we actually go to the actual data structure stack, we envision the data structure to actually look like this, a stack of things. And then we can actually, start to take things out of the stack. And in a physical stack, mostly, in an actual stack of books, you can actually, try to remove this computer science 1 book, even though you have a computer science 2 book on top. Actually, you can do that, right, in real life. But for the data structure, you have restrictions. For the data, we will see that later, but you have restrictions that you can only remove something that is on the top of the stack. If you want to remove computer science 1, you have to remove computer science 2 first, and then you can reach over here. But basically, just for now, let's think of stack as like, one thing on the top of the other. And technically, when you're talking about recursion, behind the scenes, it's just a stack of function calls that exactly looks like this, that calculates the result of the recursion. So we will see that with the help of an example. So on the Titanium, you have a code that has been posted, which is recursion examples for factorial and sum. If you click that, then you have something called some functions that are written over here, 3 functions. If I minimize them, in the main function, I have an integer n. Then I'm saying that we want to find the sum of first n integers, and I'm telling the user to enter n. So the user will enter n. So maybe the user enters 5. Then I call the iterative sum function, and that function is called sum I with the argument that I just received, n. So maybe I passed n. So sum I with, I passed 5. So sum I with 5 was called over here. So when sum I with 5 was called over here, then this function becomes active over here, sum I. And then 5 that was passed over there, 5 gets passed over here. And this is an iterative version. That's why I'm calling it sum I. Iterative version always has loops. So either a for loop or a while loop. So what I do over there is outside the for loop, I just set total to 0. Then I run the for loop starting I at 1 and go till n. So because I want to find the loop, the sum of first n integers. And total is just 0, some variable, where I keep adding subsequent i's. So I'm adding I as 1 first to the total, then 2, then 3. But that's what I want to do. I want to total all of them together. This is what I do inside the for loop. And then finally, when I'm done in the for loop, outside the for loop, I return total. And this will return the sum of the first n integers, right? But this is an iterative version. So is this clear how this is working? Now, if I want to write a parallel, I mean like a recursive version of this sum, then let us see how what the code looks like. The recursive version intuitively just follows the exact formula that we got from the slide over here, which is easy to see. This formula over here, that sum n is equal to n plus sum n minus 1, but that's what you do. You took 5 plus the same thing done for the 4, the same thing done for the 3, and so on. What you have is the base case is that it will eventually stop. So even if in the beginning you had n is equal to 1, it's going to return a 1. But for all of the cases, it's going to actually, if you pass 5 in there, it's going to say, okay, 5, and then do the same thing if you were to add the first 4 integers and then call it with 4, because it's calling itself. That's the recursive function, it's calling itself. So when it calls itself next time, it will do 4 plus, and then it will do sum 3. This will keep repeating until it reaches over here when it says return, and the function calls will start returning. And then eventually when the final return, you'll get the answer. In the behind the scenes, what happens is let me share my iPad over here so I can draw better over here. Can you see my screen?
Yeah.
Yeah.
Okay. So look at the function. You can open up the program on your end and then look at what the function is the recursive sum function is doing. So if initially it is called with the sum r is called with 5, what happens behind the scenes is a stack is in the memory, in the RAM. Mostly you will have a stack that will store the respective the subsequent function calls. What happens is it checks if n is equal to 1, n is not equal to 1, it's equal to 5. So what this will do is it will actually store the call over here at the bottom of the stack with sum r5. And that says that if n is not equal to 1, because you go into the else, you will say return 5, that is n, right? Return n plus, then sum r, n minus 1 is 4. This is the eventual return. This is the answer you're expecting out of this particular point, but it's calling yet again the same function. So technically you cannot just return the answer yet. The sum r again generates yet another function call. So that call has to be stored over here as a stack on the top of the last entry of the stack, which is now over here. That would do sum r4. This will again do, because now currently your n is 4, because you're calling it with 4. So when you call it with 4, n takes the value of 4. So that will now treat n as 4, and then you will say sum r4, you will do n plus n minus 1, so which is 4 plus sum r3. Again, sum r3 does 3 plus. So you have these subsequent, it's not stopping yet. You are generating subsequent calls. Sum r1. Finally, when you go to store the call for the sum r1, and now it's called with 1, n is now 1. And it goes to if n is equal to 1, yes, it is equal to 1. So it's not calling the sum function again. It's actually returning 1. When it returns 1, this top of the stack, entry on the top of the stack that you have gets erased, and it returns 1 over here. So technically 1 is the value that is returned over here, because the call was asking for sum r1. It returns the value 1. And that 1 can be added to 2 over here, because this 2 was waiting for this call to return. So 2 plus 1 is now 3. This call is complete, and this returns the value over here, which is 3. Now 3 and 3 are added, you have 6. This call is complete. So you have 6 over here. Now 6 can be added to this 4, you have 10. This call is complete. And it is returned over here, 10. And then 10 plus 5 is 15. Now you basically have the answer for the original sum r5, which can return the value 15. That's exactly how behind the scenes the recursive function will be calculating your sum r5 through a series of recursive calls which are stored on a stack. Is this clear? Any questions at all? Okay, so what we see over here is now we have seen how this recursion is doing the same thing what we were trying to do in the iterative version. The factorial is very similar to the sum r function. All you have to do is look how similar it is. The base case is the same. Only thing is, like, your name of the function is different. It's called fact r. But this time, instead of adding, you are multiplying. Because in the factorial, that's the formula. But now you can see how recursion is actually calculating these things over here. Now the point remains is that these things are independent to what our class is basically. So these are mathematical formulas. You can write independent code for it, for factorial, for sum. But what if we want to add code to the classes that we have seen? So we have seen how we were writing the code for the calculating the length of the singly linked list, that is the number of nodes in the singly linked list, using the iterative version. What if I want to write the similar function to this, but a recursive version? So doing the exact job that this does, but I want to write a recursive function for it. So let's go first of all, just a recall of how to add a function to the singly linked list. We can click on Visual Studio, create a new project, and then this is a console app. Then I will save it in my 131 folder. And then let me call this project just SLL. The default C++ file, source file that comes with it, you can actually just Control A, select all the code in it, and just hit delete. And then you can take the example, main function example that we have from the Titanium, which is the S linked list example. Copy the code from there and paste it in the source file, because this one builds a singly linked list based on the GitHub classes. So this is a code that you can actually use just to test your newer functions. Now, because in order to run it, we have to add the S-linked list files over here. So I showed you how to download the GitHub code. You can actually go to the GitHub source code, click on the code, and then click on download zip. Then you can save that zip file to whichever folder. I have it in my 131. This is the zip file. Then I unzip it over here. And then here are all the files on the GitHub. Now make sure you just copy the files from here. Don't change them, just copy them from here. Don't cut them. Simply Control C and bring them to your current project because you want to attach it over here. So in my SLL project, I will paste them over here. And then I will have to attach it in the header files in this Solution Explorer. So I'll right click, then click Add, Existing Item. So we have this ready to go. Now, this list we have ready to go. So we have a few items in the list, but you can add more nodes in the list, you can simply call appends, prepends, wherever. So I'm adding more nodes in the list over here. Currently, these have 6 nodes, and then I can run it to see my list is this one over here. Now from the titanium, where I have my uh, get length function that we did in the class last time, and we have I posted it here. This is the iterative version. So I can simply copy this function and then paste it. I want to put this in the hxx file. Right before just the iterative functions, let me paste this over here. To make this work, I also need to put the header in the HPP file. So I'll bring this over here. I don't need the class name in here because it's inside the class. So now this is ready to go. This get length I is one that I've taken from titanium. Let me test this. Let me call this function in the main function. So the object is SLL, and I call it, then I call get length, and I run it. You can see it correctly results 6 because there are currently 6 nodes in the list. Now I want to actually write a recursive version of this one. So in order to write the recursive version of this one, what I'll do is first I should have the template line. Then I should have the function header. Let me call it get length R because it's recursive. And I need to put this header in the HPP. Okay. So now this get length R. So for calling the get length R, we can try to begin with the same code over here. So what we have, because we have to begin at the head because we are counting the nodes. So we will begin at the head, right, of the list. So simply we have to do this nodes. I'm just copying this code from the iterative version where I have node star pointer equals head, which I do this over here. And now I need to be able to call this function with the, because this is a recursive version, so I need to be able to call this function over here. I need to call this function over here to make it recursive. But the thing that we have seen in the factorial and some examples is in the recursive versions, we successively update the argument. That's how the recursion is actually working, going over to the next step. Because we started at n, we went to n minus 1. N minus 1 will lead to n minus 2 eventually. It's decrementing, it's going to the next number. Same case for factorial. That means that you have to pass a subsequent argument to this function for it to keep working for the next one. But our function does not have an argument over here. So if I want to call this with something, maybe pointers next, because I want to go to the next one, right? I want to add that. That's what we are trying to do in the while loop as well, going to the next. So if I want to call this function again with the pointers next, I need to send an argument over here. If I send an argument, that argument needs to be received over here. But if I have this provision of receiving it over here, maybe I have something like this over here, the same case like n and n minus 1. The point begins that I am going to call this function in the main. If so I will be calling this function in the main. But if I have to call it in the main, and it will be called with something over here, what will I send over here? What pointer will I send over here? I need to start at the head. Is head available over here? Can I do something like pointer? Can I just pass head over here? Because I need to begin at the head. The thing is that this SLL is an object of this class. It's an object of this class, so it can only access the public members of the class, never the private members. Underscore head, which is the head of the linked list, is a private member that we can see over here. It's a private member which is available only within the confines of this class. This is the confine of the class. This class begins and ends over here. So technically, all the functions inside it can access it, but anywhere outside, which is the main function, which is the object, has no access to the head because it's a private member. So if I cannot access the head over here, I have no way to access head over here. All I can, it's an existing list. I cannot pass anything from externally to sort of begin this function at the head, because I need a pointer over here so it can successfully call the pointer, because if I have to have this function call work like that. So technically, how to solve that problem? I need to have a 0 argument function over here so I can call it in the main. But I need to have a 1 argument function over here so it can call itself. So to do the job, I will have to have 2 functions. One, a public 0 member function, 0 argument function, which matches exactly like the one that I'm calling over here. This call will call this function, which is a 0 argument function. In that function, what I do is, similar to the iterative version, I have a temporary pointer to the node. I set the pointer to head because this function can access head because it's a part of the class. So inside this function can access the head. So we use the head to set the pointer, and then we call a helper function. The helper function will be called with the head. So now we can access head, which this function was not able to access over here in the main. This one can access head, so we pass the head to it. We call it the helper function. And then this helper function will do the job. This is a private helper function which is not available outside the class. So we will actually, first let's write the header for the skeleton for the helper function, which will be similar to this one. And then this will take in a type of node star PTR because we are sending pointer to it. And it will return also the same thing, a type size t. When it will return the value, it will receive the value over here, line 304. But this one will again return what get length r should return. So we should have a return over here. And then we need to have have the header in the HPP for the private helper. So move it in the HPP. But this is a private function, so we'll put it in the private section. In the private section here. So this is a node star. This takes in an argument node star. Now in the helper function, what do we write? We can take hints from the iterative version where we are doing something as long as the pointer is not equal to null pointer, which means that if the pointer is equal to null pointer, something will happen. It will stop because when the pointer, as long as it's not null pointer, it's running, the while loop is running. But when the pointer is equal to null pointer, it's exiting the while loop. So in the same thing, if the pointer begin with the base case, that will actually stop the recursion. If the pointer is equal to null pointer, so just take the lead from the get length over here, where it says the base case is when the recursion does not work, when you have an empty linked list, which means that if the pointer in the beginning was actually, just directly pointing to null pointer, then it's an empty list. Then you return 0 because it's an empty list. But for all other cases, when the pointer is not equal to null pointer, what are you doing? You are incrementing some counter every time for each node and also going to the next node. So basically what you're doing over here is you want to do that using recursion. Using recursion will actually call the same function, which is itself, but with the updated argument. So for factorial and sum, it was n minus 1. For the length, what you're trying to do in the while, you're going to the next over here. So you'll copy that pointers next because you're updating the pointer to pointers next. But merely returning this will not help. What you're doing at each step, because this was a sum of one node and then the rest of the list. So that means that you are currently on a certain node, which is what you are on. So this will do 1 plus go and do the same thing for the rest of the list. This is your recursive call. What this one does is, if this is a singly linked list, if this is a singly linked list, in your public function, what you did is you set a PTR to the head, And then you call the helper function with this PTR. What the helper function does is it checks, is the PTR equal to null? In this case, not yet, no. So what it'll do is it will add 1 for the current node it's on. So this is that 1 for 3. We'll add 1 for the current node. And again call the same function with pointers next like this. So now your pointer is pointers next. So the same function is now called with pointers next with this particular pointing over here. You'll again check, is it null? No. So then return 1 plus. So it's counting 1 plus now 1 for this node. So for this node, another 1 is counted over here. And again, it goes pointers next, sets pointer to this one over here, and calls the same function to pointers with pointers next. It reaches here, it says, is it null? No. So again, 1 plus, so counting this node, 1 plus, then again, pointers next. This time pointers next is null. So it's null, so it will call it with null next time. It calls it with null next time. Now your pointer is equal to null, so you will return 0. So this will stop here. Once this stops here, then you return 0, and then it's happening in a stack. So this is by reverse calculation will happen. When it will return 0, then 0 goes on to add to 1. You result 1 out of it. Then this 1 gets added to 1 over here. 2 is resulting out of it. Then this 2 will get added to 1. 3 gets out of it. And then the final thing will return as 3 over here. And then this will then return, 3 over here, which you will receive back in the main for this list. So if I'm now trying to work this on my current list, let me run this with the get length r and see if I get the same result as the iterative. You can see that I get the correct answer. Now, is this clear? Any questions you have?
No, it's clear.
Okay. So what I can do is give you a small exercise over here where you have to use the same logic to write a recursive function. But then you have to write a recursive function to find the sum of all elements in the linked list. So just now we found the number of all elements. Now you have to find the sum of all elements in the singly linked list. So I can make this function available for you, the length function that I was just writing, the recursive length function. And you can use that to gain insight into how to write the sum of elements.
That helps, Professor. Thank you.
So let me actually then move you into some breakout rooms, and then you can work on it. So just remember your group number, the room number. Only we have few people, so only 2 rooms. Group 2. Is it what? Who is typing? Johnny or Eric? Both of
Uh,
you from group 2?
well, I got my own, and then Eric got his own, but we didn't have enough time to talk it out, so maybe we can just take a look at both. I don't know. Or you can pick out which one looks closest to the actual answer, and then maybe
The
help
thing
us.
is that, Johnny, what you're trying to do is you are making the head accessible in the public function in the sum. Like I
Yeah.
said, if we call this function in our main function and sum function in the main function, we will not have the access to the head over there. So is
Mm,
this your helper function or is this your, because we had to write two functions. So basically, if
mm,
this is your helper function, even then you should not be calling it head. You should be calling it some other name,
okay.
PTR or temp or something.
Okay.
And then that would have PTR pointer data, not just PTR, not just data.
Okay.
But this is mostly your private function, not your helper function.
Okay.
Now what Eric has is let me just look at it. So what Eric has is sum is equal to, so you have two steps over here. Sum is equal to pointers data with the, you're doing two things. You're calling the sum helper function twice. In one case, you're actually returning the number of the count of the total nodes. In the next case, you're actually adding. You just
Yeah.
had to do just one function.
Yeah, I realized that. I was like going kind of fast because I got the thing that said the breakout room was going to end in 50 seconds. And I knew I had to do something with sum, and I knew I had to separate the data from the pointer. And so that's where I like had stopped. I wouldn't have left it like this.
Right, okay. So just the first line is correct inside that the recursive call. And this one is Fabian, this is group 1. So you have, which is correct. No, but you use this, but you in the recursive call you have to do pointers data. Pointer arrow data.
Oh, yeah. And in the return.
Yeah.
Oh, that's right.
And you
Yes.
have a lot of surplus this that you don't want to have all the time. There are a lot of this are sort of redundant in these cases.
I have a question.
Yeah.
Where in the if statement, if pointer is equal to null pointer, we returned that, but we weren't sure, or I wasn't sure what to return there.
You have to return 0 over there.
But what if the data, well, I guess we're assuming that the data is an integer, right?
We are assuming a data is an integer in this case. Yeah. Well, in that case, then you are actually trying to then have some way of using the equivalent of, this is basically, yes, we are assuming something that can be added. So mostly in your nodes, you could also have classes, right? You could have classes, you could have structs, something that cannot be added technically. So we are assuming that the elements are containing integers, yes.
Or because what if the elements are containing floating points?
Yes, then you can just say return 0.0.
Exactly. So I have to assume.
Yeah, maybe it will say in the question that assume that. Because the sum only makes sense sense only in terms of either decimals or integers. You cannot sum, there's no sense summing characters or any other things that you might have in the list. But this is just to technically, learn recursion, not to, I mean, like, there are cases where you cannot sum those things, but then we'll not be writing functions for those kind of lists. I mean, we can, but this function is mostly just catering to something that you can sum. Let's put it that way. The idea really is to learn to mostly use recursion to do that. So what we really had to do in this particular case, like we have the get length r, and then we have the get length r. All you do is like, if you simply, you can simply just copy this code, these, because you have to have these two functions. Simply copy this code and then paste it here. Just call it get sum r, and then sum r helper. And now we'll have the corresponding things in the HPP. Now look, I have the same code. The only thing that I copied the length function, so they're still the same. I changed the names. The only thing that I supposed to change was, instead of adding 1 every time, I should just add pointer arrow underscore data. That's what I had to do. So instead of the 1 in this function over here, where I had 1 because I'm counting each node, now I'm counting the data at each node. So I have pointer arrow data, because it gives me the data at the node that the pointer is pointing to. So I just had to change the 1 to this one. Now I can actually run this and test this, which I would recommend that you do when you write your own functions. Test it. And then run. Let's see what it gives us. Get some r, still give me 6. Oh, because I'm calling get length helper in it. I should be calling get sum r helper. What? Oh, because I'm not calling the sum r helper here. I should be calling the sum r helper inside the sum r. I'm calling the get length helper here. There you go, I'm getting 62. So if you add these three together, 39, 3 times 39, 13 is 3 times, so you have 39, then 10, 49. And then 9 is 58, and then 4 is 62, which is correct. So you get the correct answer. You should test this basically on some linked list to see if you have the correct answer. The point being that you had to change very little in the length versus the sum. All you had to change is the 1 to the pointer arrow data. Everything else is exactly the same. Now, any questions at all? So is this clear all completely? How we write recursive functions to the linked lists? So all right, we can then wrap up and then meet again. Just remember that you have to finish your project by this Sunday. And you also have a homework that's due next Tuesday. I'll be posting more another homework, but that will be due next Sunday, which will have a couple of cursive functions to write.
Well, Professor, I was wondering if you could extend out the due date for one of the assignment that's due on Sunday, because it seems like a lot within 1 week.
The assignment that was originally due on Sunday was already changed to Tuesday. So there was a homework that was due the same day on Sunday, but now it's due on Tuesday.
Okay.
There's no other homework that is due on Sunday. There's only one project that's due on Sunday.
Can we have more time on the project?
We cannot have more time because